Okay, Assalamualaikum and salam sejahtera. Okay, so today we will talk about the our new chapter. Okay, the Earth. Okay, so in this chapter we will learn about the overall structure of the Earth's atmosphere. Okay, Earth's interior, the surface activity, Earth's magnetosphere, and lastly about the types. Okay, for the overall structure of planet Earth, okay, we have mass, radius, and density, and also the density of water, the density of rocks. Okay, so with this mean density known, we can deduce the denser material must lie deeper under the surface. So the composition of the Earth was studied using aircraft, satellites in orbit, gauges on the land, submarines in the ocean, and drilling gear below the rocky crust. Okay, let's go into the regions. Okay, in our Earth, so there are 6 main regions here. Okay, if you can see in this figure, you have the inner and outer core. Okay, about 1,300 and 2,200 kilometer. Okay, so the mantle. Okay, here the mantle layer origin 2,900 kilometer. The crust. Okay, crust 5 to 50 kilometer. The hydrosphere, okay, contain 70% the water. Atmospheric layer, okay, and lastly we have the magnetosphere. Okay, so the gaseous atmosphere and magnetosphere contribute less than 0.1% of the total mass. Okay, so now let's talk about the atmosphere composition. So you have nitrogen, oxygen, argon, and carbon dioxide with their percentage of the composition of each gases, and the water vapor varies from 0.1 to 3% depending on location and climate. So the presence of a large amount of oxygen makes our atmosphere unique in the solar system. So now we go to the atmospheric structure. Okay, we have 4 different layers. Here, if you can see, the bottom one is less than 12 kilometer, which is the troposphere. And then going to stratosphere, about 12 to 50 kilometer. Okay, 12 to 50 kilometer. Followed by the mesosphere, you have around 50 to 80 kilometer here. And lastly, we have the ionosphere. Okay, so larger than 80 kilometer. Okay, above than 80 kilometer. So each different layers contain or consists of specific content. Let's say here, the stratosphere. We have the ozone layer here. Okay, so in between the stratosphere and troposphere, we have the clouds and also the water vapor. So atmospheric density and pressure decreases steadily with increasing altitude. Okay, so that is for density and pressure. Okay, now we go to the convection process, which is happen in the troposphere. Okay, the process that physically transfer heat from a lower, hotter to a higher level. So the lower level represent the hotter one, and the higher level is represent the cooler. Okay, so this contribute to the atmospheric heating. okay, surface winds, and all the weather we experience. So all about the convection process. So the atmospheric convection can also create clear air turbulence, okay. And for example, the passenger aircraft tend to fly above most of the turbulence. At the top of the troposphere or in the lower stratosphere, where the atmosphere is stable and the air is calm. Okay, now we go to the ionosphere layer. Okay, so it's significantly ionized by the sun's high energy radiation, which breaks down molecules into atoms and atoms into ions. So the degree of ionization will increase with the altitude. Okay, so a good conductor of electricity will highly reflective to certain radio wavelength. For instance, the AM radio can reach over the horizon. Okay, how about the ozone layer? So the ozone layer is an altitude approximately 25 kilometers within the stratosphere. So incoming solar UV radiation is absorbed by atmospheric ozone and nitrogen. So the UV radiation breaks ozone down, forming molecular oxygen. And the ozone layer is one of the insulating spheres that serve to shield life on Earth from fierce radiation and energetic particles, both of which are injurious to human health. Okay, how about the CFC, or we call chlorofluorocarbon? Okay, it's a use as propylene in aerosol cans, solvents in dry cleaning product, and coolant in air conditioner and refrigerators. So normally it is found in the refrigerators. Okay, so it's accumulate in the atmosphere and are carried high into stratosphere by convection process. So it will be broken down by sunlight to release chlorine, which acts as a catalyst to turn ozone into oxygen. And this also can break down 100,000 ozone molecules before being removed by the other less frequent chemical reaction. So it's extraordinarily efficient at destroying atmospheric ozone, resulting in a substantial increase in UV radiation level at the Earth's surface with detrimental effect to most living organisms. So it's a very dangerous type of gas because it's released the chlorine, okay, and act as a catalyst to turn ozone into the oxygen. So it will break down by the sunlight. Okay, now we go to the ozone hole. Okay, a vast ozone hole is found over the Antarctic with ozone level 50% depleted. Okay, so you can see in this figure the center of the ozone hole. Okay, so the low temperature at the Antarctic created a vast circumpolar cloud of ice crystals that act to promote the ozone destroying reaction. The smaller holes are observed in the Arctic with up to 20% ozone depletion. So it takes decades for all CFC to leave the atmosphere entirely. So it's very, very slowly it's very slowly processed to remove this CFC from our atmospheric layer. Okay, because it takes about a decade, okay, to be omitted in our atmosphere. So it's very bad impact to our health, okay, to our health and also to our climate. Okay, so for the color of the sky, okay, Earth's sky will look blue due to the light being scattered by air molecules and minute dust particles. Okay, so what is the scattering? Scattering is the process by which radiation is absorbed and then re-radiated by the material through which it passes. So for the Rayleigh scattering is the predominantly elastic scattering of electromagnetic radiation by particles much smaller than the wavelength of the radiation. Okay, for the blue light, 400 nanometer in wavelength is much more easily scattered than red light, okay, about 700 nanometer, because the wavelength of blue light is closer to the size of the air molecules. So for the air molecules or the small particles, the amount of scattering is inversely proportional to the fourth power of the wavelength. So this is their relation. Okay, but for dust, okay, large particles, dia punya relation is the scattering depends only inversely on the wavelength. Okay, so when the sun is high in the sky, okay, blue light is scattered much more than any other colored light. Therefore, the sun is reddened slightly, whereas the sky away from the sun appears blue. So for down or dust, the blue light from the sun is almost entirely scattered out of the line of sight, while the red light is diminished in intensity. Therefore, the sun appears orange and the sky appears red. That is the process. For the sky, we observe or appear as an orange color, and the sun appears in orange color, and the sky appears in the red color. That is the explanation. So much of the sun's radiation penetrates the Earth's atmosphere and reaching the ground in the form of visible and near infrared radiation and heats up the Earth. So as it heats up, the Earth's surface re-radiates much of the observed energy like a black body, and the amount of energy radiated increases with increasing temperature. That is the Stefan's law. So in theory, the Earth should achieve an average surface temperature about 250 kilometer. Okay, what the Wien's law state? Okay, most of the re-emitted energy at this energy is in the form of infrared radiation according to Wien's law. Okay, so this re-radiated IR radiation is partially blocked. Okay, re-radiated here. The red color represent here is partially blocked and absorbed by the air molecules of the water vapor. And carbon dioxide in Earth's atmosphere, even though they are only trace constituent. So only some of the radiation escape back into space. Okay? Only some of it will escape into space, and the remainder is trapped within our atmosphere lah. Okay, and this causes the temperature to increase up to almost 40 degrees. So this partial trapping of solar radiation is known as the greenhouse effect. Okay, so there are several or four the gases that will trap or will cause the greenhouse effect, okay, which are carbon dioxide, water vapor, and methane. So due to the burning of fossil fuel, okay, the carbon dioxide level have increased by over 20% in the last century, and they are continuing to rise at a present rate of 4% per decade. So this will increase in carbon dioxide level in our Earth will result the global warming, rise in sea levels, and accelerated spread of disease. Okay, so when the Earth was first formed about 4.6 million years, so its primary atmosphere might have consisted of the common gases in the early solar system. which are hydrogen, helium, methane, ammonia, and water vapor. Almost all these low-density material will escape into the space during the first half billion or so years after the Earth was formed. But subsequently, the Earth developed a secondary atmosphere, which was expelled from the planet's interior as a result of volcanic activity. Okay, so this volcanic activity rich in water vapor, methane, carbon dioxide, sulfur dioxide, nitrogen, ammonia, and nitric oxide. Okay, for this solar UV radiation, split the lighter hydrogen-rich gas into their component atom, allowing the hydrogen to escape and liberating much of the nitrogen from its bond with other elements. So it's creating the atmosphere consisting largely of the nitrogen gas. So as the Earth's surface temperature fell, the water vapor condensed to form oceans. The carbon dioxide and sulfur dioxide will be dissolved in it or combined with other surface rocks. But for the oxygen, however, is very reactive. Any free oxygen that appeared at early times will be removed as quickly as it formed. Okay, so the life appeared in the oceans more than 3.5 billion years ago, and organisms eventually began to produce atmospheric oxygen. So how about the ozone layer? The ozone layer was formed, shielding the surface from the sun's harmful radiation. So the life spread to the land and flourished, oxygen being a major constituent of the present-day atmosphere is a direct consequence of the evolution of life on Earth. Okay. Next, the indirect probes are required to study the interior of the Earth, since no substance used for drilling can withstand the pressure below a depth of about 10 kilometers. Okay, so what is the earthquake? The earthquakes will cause a sudden dislocation of rocky material near Earth's surface, and the vibration produces seismic waves that move outward from the site of the quake. So the seismic wave can be detected and recorded with a seismograph designed to monitor Earth's tremors. Okay, so let's see the seismic wave, which are divided into two. I think there are primary wave and the secondary wave. Okay, so for the primary wave is the first to arrive at a monitoring site. They are pressure waves that alternately expand and compress. Okay, as you can see, there are process of expansion and compression here. Okay, the core or mantle through which they move. So this is the wave motion. Okay, travels at 5 to 6 kilometers per second, depends on the medium, and it can travel through both liquid and solid. So let's say the particle motion was like, okay, with let's say you have particle here, so the particle motion will be like a cycle, okay, and move like that. So this means the high density and the low density in the process of expansion and compression. So how about the secondary wave, or we call S wave? It comes sometime later than the primary wave. They are shear waves that cause side-to-side motion. Okay, so the motion is something like this. So it's like a vertical motion here. The particle travels at 3 to 4 kilometers per second and also can travel through solid but get absorbed by the liquid medium. Okay, so if we can measure the time taken for the wave to move from the site of an earthquake to a monitoring station on the Earth's surface, so we can determine the density of matter in the interior. Okay, so the wave, however, do not travel in straight line through the planet, since the wave velocity increases with depth. Okay, so the important result here, the seismic station on the side of Earth's opposite a quake never detect the S wave. The P wave always arrive at station diametrically opposite the quake, and part of Earth's surface receive almost no primary wave. So deduction, when the secondary wave are absorbed by a liquid core at the Earth's center and the primary wave are reflected at the core boundary, resulting in a shadow zone. So the size of shadow zone will depend on the radius of the core, and the collected seismic data yield a core radius of about 3,500 kilometers. Okay, for the modeling Earth's interior, if geologists accumulated data about shadow zones and seismic wave properties all over the Earth and used them to build mathematical models of the Earth's interior. So as we can see, we have crust, inner core, outer core, and mantle. So let's see the graph here. We have density graph and temperature. So when the depth below surface, okay, when you have very high depth, about 6,000, okay, from the surface, so it's very inner part, the temperature will be very large, okay, here for the yellow area. And same goes to the density. If the depth below the surface is very going down or very near to the core, so the density also very large. Okay, so we go to the crust here. Okay, the crust part. So it's average thickness of 15 kilometer. Okay, and the average density 3,000, and average temperature is 300 Kelvin. Made of mainly granite. Okay, granite is a mixture of silicon and aluminum oxides. Lighter material than the mantle, allowing it to float atop. Okay, so how about mantle? Mantle accounts for 80% of our planet's volume. Average density is 5,000 and made of dense rocky material. Compounds of silicon and oxygen based on the observation of chemical and physical properties of newly emerged lava from volcanoes. So the upper mantle is made of basalt, okay, iron, magnesium, silicate mixture. Okay, so next one is the core. So average density is very high, 12,000. Temperature also very high, 5,000 Kelvin. Okay, so it's equal surface temperature of the sun. So it's very high temp and very dangerous region. We can say in the structure of the Earth. So high density suggests that core is made of compressed mixture of nickel, iron, and sulfur. So the materials between the outer and inner core simply changes from the liquid to solid state, but much of the core must be a liquid. And high pressure forces material to be in solid state despite high temperature. Okay, I think that's all for you who not come in the class because of the clashes with the other subject. Okay, so you can refer to this slide, slide 1 until slide 29. Okay, thank you.